I'll give you 2 minutes.
Yeah.
All right, our next speaker is Ethan Carter, and he's talking about radiative transfer and the properties of disk instability protoplanets. Thank you.
Okay, thank you. So, hi everyone. As Rebecca already introduced me, I'm Ethan Carter. I'm from the University of Central Lancashire in the UK, and I'm here to talk about my ongoing PhD work on the effect of radiative transfer on the properties of disk instability protoplanets. So I'll give a very quick introduction to giant planet formation here. So there are two kind of main theories for forming giant planets. The first which I'll talk about is core accretion. Core accretion describes a bottom-up approach to forming planets, where essentially you form a solid rocky core through kind of collisions between planetesimals and accretion of pebbles. And then this core will accrue gas over time, ultimately forming a giant planet. Core accretion is really good at predicting the formation of close-in giant planets, kind of within 10 years, typically a hot Jupiter population, for example. However, as George already mentioned, it requires a relatively long timescale to form giant planets, which is at odds with the expected disk lifetime. And the kind of alternative approach to forming giant planets is that of disk instability, which is what I'm going to focus on today. So disk instability instead takes more of a top-down approach to planet formation, which I'll explain a bit more about in a minute. So thermal and rotational support, then the disk will be gravitationally unstable and form strong spiral arms. If the disk can also cool sufficiently fast enough on a dynamical timescale on the order of a few orbital periods, and then the disk will fragment, forming dense clumps of gas, which will collapse on a relatively short timescale, forming a giant planet. Disk instability is really good at explaining the formation of wide orbit giant planets, although it does predict the formation of more giant planets than we currently observe. Which is kind of one of the issues currently. And as I mentioned, this is kind of much faster, so it's within our expected disk lifetime as opposed to core accretion. And when planets form by disk instability, they undergo more a star-like formation pathway, more akin to the evolution of kind of low-mass stars and low-mass star formation. So this is a plot here showing log temperature, and this is log density for a 1 solar mass core in red and a 1 to kind of a few Jupiter masses fragment in this lightly shaded region here. And essentially from bottom left to top right, we can follow the evolution of our core or fragment. And essentially we have a initially isothermal collapse until the fragment reaches a central density of around 10 to the minus 13 to 10 to the minus 12 grams per centimeter cubed, at which point the fragment becomes optically thick and begins to rapidly increase in density and temperature. It will also collapse until we have a pressure-supported core, which we refer to as the first hydrostatic core. This first core will then continue to accrete material and grow both in temperature and mass until it reaches a central temperature of around 2000 Kelvin, at which point H2 begins to dissociate. At this point, the protoplanet or fragment is no longer stable. We have a second collapse and form a slightly smaller second hydrostatic core. And as shown kind of by recent work by phantom2025, it's been shown that these disk instability protoplanets are not necessarily spherically symmetric like you'd think, but are in fact somewhat flattened, or in other words, oblate spheroids. So this is two plots from their work showing a cross-sectional slice through a protoplanet, essentially showing a top-down view in the XY plane on the left, and then looking at a egg-on view, so kind of the vertical profile on the XZ plane here. And as you can see on the left for our kind of top-down view, we've got a nice circular gas profile, actually notice that the arrows indicate the gas velocity, kind of typical what we'd expect from our spherical protoplanet. However, when we take this edge-on view, we see this more of a flattened kind of oval shape, and we also see this enhanced infall onto the poles of the protoplanet, which may have significant implications for not just its evolution, but also its chemical composition as well. So I'm really excited to see George's work progress with regards to them. One of the results that they also found from their work is essentially the first cores that I mentioned tend to be highly flattened, whereas the second cores tend to be almost spherical. So there's a histogram here essentially showing how likely it is for a first core in blue or second core in red to have a given aspect ratio. So with the far left towards 0 being highly flattened, and then kind of around 1 would be perfectly spherical here. So you can see the blue, so the first cores are tend to be highly flattened and more across this kind of half. And then for the second cores, we have kind of a peak around this 0.8 to 1 region, showing that they tend to be more spherical. And I'll show this again later. However, kind of one caveat with Tensor Stamtels 2024, and something that I'm glad to see a lot of people seem to be considering a bit more now, is they made massive simplifying assumptions with regards to the equation state they used to govern the heating and cooling in our simulations. So they used and I believe it's still quite common, a barotropic equation state. And a barotropic equation state only roughly approximates the heating and cooling of the disk through assigning a parallel relation between temperature and density. So this is plotted showing log temperature to log density and the barotropic equation state in blue. And kind of at best, you might have what they use, which is a piecewise barotropic equation state, where you assign a varying power law or hard-coded turnoffs to try and replicate what's actually happening in your fragment. And the main issue with this is that when you use a barotropic equation state, you're assuming that the thermodynamics in the disk behave the same everywhere, regardless of the local environment. And ideally, we'd like to model this using kind of full rate of transport, but as we all know, typically you have to couple it to something like MC fast, or do some kind of post-processing. However, an alternative approach is to use a rate of transfer approximation method, which allows us to treat the thermodynamics in the disk in a more realistic way than the barotropic equation state, because we consider the local environment, but without kind of massive additional computational expense, and that's shown by this red line here. I'll give a very brief overview of how this works in simulations. Basically, the rough idea is that for each SPH particle, we assume that particle is embedded in a pseudocloud, or essentially a parcel of gas. And for each of these parcels of gas, we estimate a weighted mean column density and weighted mean opacity from a particle to the surface of our parcel of gas. From that, we can determine a new rate of heating and cooling. And from that, we can then update the temperature, density, and energies of our particles in our simulations. And there's a few different approaches to this now. They all work fundamentally the same way, regardless of the parcels of gas. The main difference is how they estimate the column density and the opacities. So this is a wonderful plot here that was from Alison Young's paper, Young's 2024. And this is just showing the log column density for a disk simulation with respect to disk radius. And you can also see that we have this large peak here, and this is the presence of a protoplanet or a fragment in a gravitationally stable disk. And each color is essentially just showing the different approaches to our rate of transfer approximation methods. So we have the kind of the original Stamtels et al. Method, which used the gravitational potential to estimate the opacity and column density. Then came along the Lombardi et al. Method, which instead used the pressure scale height. And this is because while Stamtels method gives a very good estimation for kind of our fragments and our clumps, using the pressure scale height gives a better estimation kind of elsewhere in the disk. And then, as I mentioned already, Alison Young had developed and implemented the combined method, which essentially just alternates between Lombardi and Stamtels methods in the regions that they work best. And also the modified Lombardi method, which uses relatively simple disk geometry to estimate the column density and opacity using a disk geometry. So it's well tailored to kind of self-gravitating disks. And essentially here, I want to talk a little bit about what I've actually been doing with my work in the context of this. So what I want to do is I want to investigate the effect of using a more realistic equation state on the properties of disk instability protoplanets. I want to do this by simulating a massive gravitationally unstable disk using 4 million particle simulations in Phantom. I need this high particle count so I can resolve what's happening in the protoplanets, essentially. So these are very computationally expensive. And I also treat the heating and cooling of the disk using the Lombardi rate of transfer approximation method. So the one that uses the pressure scale height to estimate the column density and opacities. And this is just showing the disk evolution from one of my simulations here. And essentially, minus conditions are set up not necessarily in a realistic way, but such that the disk very quickly becomes gravitationally unstable. and we form many fragments on a relatively short timescale. With the idea that these fragments also evolve very, very rapidly. And the idea is that each of these fragments is that we can then follow the evolution through each order of magnitude density as a proxy, kind of for looking at the evolution through time, until the central density reaches 10 to the minus 3 grams per centimeter cubed, which is approximately just after the formation of the second core. And this is kind of one of the initial results from my work here. This scary looking grid plot here is essentially just showing the log density, log temperature, rotational velocities, and inflow velocities of 2 protoplanets. So the solid lines are those from one of my simulations, which use the slightly more realistic Lombardi radiative transfer approximation method. And then the dotted line is one of the protoplanets taken from phantom2025, which use the less realistic barotropic equation state. And although we see somewhat similar, oh, sorry, I should also mention the colors here. We're essentially just looking at the evolution of the protoplanet through time by looking at when its central density is reached 10 to the minus 9 in blue, 10 to the minus 6 in green, and 10 to the minus 3, so the end of life follow its evolution in red. And we find that simulations formed with the kind of less realistic barotropic equation state tend to overestimate the temperature, rotational velocity, and inflow velocity of our protoplanets. In particular, I want to draw attention to the temperatures first. But we have later on the evolution, we have kind of this overestimation, especially kind of radially outwards towards the extent of the second core, so just before the start of the first core. But I also want to really highlight that early on in the evolutions, this blue line here, we have a difference in the temperature of an order of magnitude, which could have very significant implications for not only just the evolution of the protoplanet, but what's happening with regards to the chemistry as well. And we also see higher rotational velocities, which indicate that the planet's rotating faster. So we find that simulations of the more realistic creating state, we expect to produce colder, slow rotating protoplanets. And we also see enhanced infall in the simulations that use kind of the less realistic barotropic equation state, which may overestimate kind of the mass and the amount of material that's falling onto our planet's evolution. And essentially here, this is just probing the 3D structure instead. So here, it's the same plots, but essentially in the black, I'm just showing a slice through the midplane of the protoplanet in the XY plane. And then in the red, I'm just cutting through a vertical slice of the protoplanets in the Z direction. And again, the dotted line is with the kind of less realistic barotropic equation state, and in the red's the kind of more realistic Lombardi radiative transfer approximation method. And again, we see kind of the overestimation of the kind of the temperature, rotational, and inflow velocities. And we also see kind of the simulations with the barotropic equation state tend to over-exaggerate how flat the protoplanet is. So we can see this by the sharper drop-off kind of between the red line and the black line here, so the Z and direction kind of through the midpoint, which we also see in the rotational velocities and for the inflow velocities. And we also see, again, very enhanced infall in the Z direction onto both the second core and first core, which you can see in the infall, the peaks of the inflow velocity here. And yeah, essentially, the point I'm trying to make here is that we need to be careful and use kind of as realistic an equation state as possible, especially when studying kind of the evolution properties of disc-instability protoplanets. Otherwise, we may get a very different picture to what, you know, is actually kind of close to what we should expect to see. And here I'll just briefly mention kind of the future work. I want to perform a statistical analysis of protoplanet properties, focusing more in detail on kind of the aspect ratios and the masses and a few other properties. And then I want to do a similar study again, but looking at the effect of metallicity on the properties of these disc-instability protoplanets. And to do all this, as I mentioned already, it's very computationally expensive because I need a very high number of particles to study the fragments in detail. I think really ideally, if we have the time, we'd already like to push our particle count formula a bit further. And so as a result of this, I'm really interested in learning more this week about the adaptive particle refinement method and how it may be applied, because I think this could be a really good use case and could be really helpful. And yeah, I'll kind of leave my conclusions here, but I will again just stress that I think for the evolution of disc-instability protoplanets, we need to make sure that we're studying them with a more realistic description of the heating and cooling in our simulations. The thermodynamics in the disk does not behave the same everywhere, like we've assumed previously when using a barotropic or even isothermal equation of state. And yeah, I just think it's something that we need to keep developing and bear in mind for the future. So with that, thank you for listening, and I'm happy to answer any questions.
Questions for Ethan? Awesome.
I know you mentioned it in the future work, but can you tell us anything about the masses you
yeah, so the question was if you can tell anything now about kind of the masses of protoplanets that I form. So these tend to be, I've only looked at this very roughly. I'm kind of waiting for more so I can do the full kind of look at the masses for our population, because it can vary based on kind of where it is in the disk, kind of how early it formed and so on. But they tend to be on the order of kind of a few Jupiter masses to kind of maybe like tens of Jupiter masses at most, for our kind of most massive protoplanets. But again, once I've done the statistical analysis, I'm hoping to literally plot a full population of this and also compare it to phantom2025's work, so I can look at the effect of varying the equation state on the mass as well to see if I am actually correct in saying that the lower rainfall onto the cores will have a notable effect on the mass.
Sorry if I've missed this. So
Yep.
At what point does the barotropic EOS break? Is it before the first core or
so
after?
Yeah, essentially what I was saying is that if you, so these are on the same radial scale up from the center protoplanet here, and this is something that I was only kind of looking at recently, but if you follow this, it's roughly the break in the, for example, the temperature here, roughly lines up with kind of the end of the second core, and it's just follow start with those core. And this is something that I want to look a bit more though before I say anything proper. The main point I'm trying to make is that essentially between kind of the barotropic equation state, and this is in this case the Lombardi method, which is what I used. Although this gives a good approximation here, this is the center of the core or fragment. As you move further away from kind of your like your clump or your fragment further out in the disk, this is where you start seeing more significant break between the red line here, which is our more realistic approach, whereas a barotropic won't move, it will stay in the same place regardless of where it is in the disk. So I think that's potentially also why we're seeing this break as well. I hope that kind of gives a rough idea.
Mike?
So as mentioned maybe earlier
Yep.
in the meeting, there are these other radiative transfer methods in phantom, like coupling to MC force,
Yep.
even proximal diffusion. Have you considered using these other methods, and do you have any expectations of how they may compare with your current method?
So there's a couple of things. So I haven't personally looked at doing this myself, but I'm really interested to see how they compare. One concern I do have is when I say that these fragments evolve very rapidly, I'm talking about on the scale of even kind of a few years or so. These fragments, especially for when they undergo the first and second collapse, and this happens on an extremely short time scale. So I'd be interested to see whether the kind of the frequency we have at the moment for the coupling to MC ethos, for example, in the wide simulations, will be able to hold up and resolve kind of what's happening during the evolution of our distance supported protoplanets.
Thanks.
I kind of have a follow-up question. So
Yeah.
SAR's work using MC force and self-gravitating disk,
Yeah.
you showed that by doing that, you can take into account if there's any structures that cast shadows, that you can then take that
Yeah.
into account for the heating and the cooling. And I know the methods you're using, they don't do that, right?
Yeah.
So, but you have quite a lot of structure in the disk. So do
Yeah.
you think that would make an impact if you were changing the local temperature because you were casting a shadow from some structure?
Yeah, I think it could. It's some things that I'd love to chat and learn a bit more about this week. I'd be really interested to see kind of Saul's approach as well.
Yeah, Mike stole my question. Any other questions? All right, we should say Ethan and the rest of the speakers